In my last video, I posed the following question. If you take n points on a circle, then connect every pair of them with a line, how many sections do these lines cut the circle into? What was strange is that when n is less than 6, and when n is 10 for some reason, the answer is always a power of 2. But for all other values of n, the answer seems completely unrelated to powers of 2. What I love about this problem is that it brings together many disparate concepts: counting functions, graphs, one of Euler's most famous equations, and Pascal's triangle. You might be wondering if changing the placement of points changes the number of sections. It actually can. For instance, watch how this small region in the middle disappears if we adjust things so that 3 lines go through the same point. But if we add the restriction that no 3 lines can go through the same point, the number of sections depends only on the number of points, not their placement, as you're about to see. I think it's fair to call this a hard problem, and in solving hard problems, it's a good idea to ask simpler questions about the same setup. In this case, I have 2 questions for you. 1. How many lines are there? And 2. At how many points do these lines intersect within the circle? For the first question, every line corresponds uniquely with a pair of points, and likewise, every pair of points gives us a unique line. Luckily, counting the number of pairs in a set is common enough in math that we have specific notation for it, n choose 2, which we evaluate as n times n minus 1 divided by 2. To see where this formula comes from, notice that you have n options for the first element of the pair, which we multiply by the n minus 1 remaining options for the second element. But this would double count each pair, so we divide by 2. For instance, when n equals 7, 7 choose 2 is 7 times 6 over 2, or 21. So there are 21 pairs of points, and hence 21 lines. With, say, 100 points, counting lines directly would be a nightmare, but we can compute it as 100 choose 2, which is 100 times 99 divided by 2, or 4,950. The number of intersection points is a bit more subtle. While every intersection point corresponds with a unique pair of lines, there are many pairs of lines that don't intersect within the circle, so we can't just count the pairs of lines. What we can do, though, is associate each intersection point with a set of 4 points on the circle, since this association goes the other way around, in that every quadruplet of points gives a unique intersection point. Just look at that, isn't that elegant? This means the number of intersection points is the same as the number of quadruplets of our n starting points. The function n choose 4 counts quadruplets in a set of size n, and you evaluate it by taking n times n minus 1 times n minus 2 times n minus 3, all divided by 1 times 2 times 3 times 4. The derivation of this formula is similar to that of n choose 2. You multiply in the number of options you have for each successive entry, then divide by the extent to which you've overcounted. For instance, with n equals 4, 4 choose 4 is 1, and indeed, there's just one intersection point. 6 choose 4 is 15, so when n equals 6, there are 15 intersection points. And if n were 100, even though the prospect of counting intersection points is horrifying, we can nevertheless deduce that there will be 3,921,225 of them. Now, how does this help us count sections in the circle, you might ask? Well, it will once we consider graphs and Euler's formula. No, not function graphs, and not that e to the pi I stuff. The word graph can also refer to a set of points, referred to as vertices, along with a set of lines connecting some of these points, which we call edges. Notice, if we count the number of vertices in this graph, then subtract the number of edges, then add the number of regions that this graph cuts space into, along with that outer region, we get 2. If we do the same thing with this other graph, well, we get 2 again. This isn't a coincidence. You could do this with any graph, and as long as your edges don't intersect each other, the answer is always 2. If edges could intersect, then you could just change the number of regions without changing the number of vertices and edges, so of course it would be nonsense. This relation is known as Euler's characteristic formula, and it's easy to see where the name comes from, since Euler's is German for beautiful. If you're curious, the reason we write f for the number of regions is because the formula traditionally refers to the number of vertices, edges, and faces of 3D polyhedra. In another video, I'll explain why this is true, but here, let's just use it to solve our circle problem. Our setup is already a graph, with n vertices and n choose 2 edges, one between each pair of points. But we cannot apply Euler's characteristic formula directly, since our edges intersect many times, n choose 4 times to be exact. However, If we consider each intersection point to be a vertex, meaning our original lines must be chopped up at these points, and if we also include the segments of the circle connecting our n outer points as new edges, we have a graph perfectly suited for Euler's formula. In particular, the number of regions in this picture is the number of edges in our new graph minus the number of vertices plus 2. Since our new graph retains the n original vertices and adds on another n choose 4 for intersection points, we replace the minus v term with minus n choose 4. To find the number of edges, note that the intersection points can be seen as adding 2 edges each, since each one takes 2 existing lines and then cuts them into 4 smaller pieces. For example, 3 lines intersecting at 2 points would be cut into 3 plus 2 times 2 equals 7 smaller pieces. 4 lines intersecting at 3 points would be cut into 4 plus 2 times 3 equals 10 smaller pieces. And in our circle diagram, our n choose 2 lines intersecting at n choose 4 points are cut into n choose 2 plus 2 times n choose 4 smaller pieces, plus another n for the circle segments we're now considering to be edges. Going back to our formula, we can replace E with n choose 2 plus 2 times n choose 4 plus n. Combining like terms, we see that our graph cuts the 2D plane into 2 plus n choose 2 plus n choose 4 pieces. Since we're concerned with counting the regions inside the circle, we can disregard that outer region and write our final answer as 1 plus n choose 2 plus n choose 4. Great, we found the answer. But why on earth does this formula relate to powers of 2 for n less than 6, then again when n equals 10? It's not just a coincidence, it has to do with Pascal's triangle. Pascal's triangle is constructed like this. Each term is the sum of the 2 terms above it. If you add up each row, you get a successive power of 2. To convince yourself of this, notice that each term is added into the following row twice, so the sum of each row should be twice the sum of the row before it. The function n choose k is closely related to this triangle, in that the kth entry of the nth row, where counting starts at 0, is always n choose k. For instance, to find 5 choose 3 in the triangle, count down to the 0, 1, 2, 3, 4, 5th row, then go in 0, 1, 2, 3, and indeed 5 choose 3 equals 10. This means that the answer to our circle problem for n points is the sum of the 0th, 2nd, and 4th entries of the nth row of Pascal's triangle. For instance, if n equals 5, we can see that we just have to add 1, 10, and 5. Since each term is the sum of the 2 above it, this is the same as adding the entire 4th row, which we know is a power of 2. Likewise, for smaller values of n, the answer is going to be the sum of the n minus first row, and hence a power of 2. However, when n equals 6, and we relate the terms to the 5th row, notice that we're not adding the entire row, since we missed that last term, so we only get 31. When n equals 10, we're summing precisely half of the 9th row, so the answer is half of 2 to the 9th, which is 2 to the 8th. So, to recap, first, turn our diagram into a graph suitable for Euler's characteristic formula by adding all of the intersection points as vertices and cutting up all the edges. Next, count the number of lines and intersection points by relating them to pairs and quadruplets of our starting points. Then finally, use Euler's formula to deduce the number of sections and then relate this to powers of 2 using Pascal's triangle.